So, hi everybody, I'm Andrea Rossi. I'm a PhD candidate and research associate at the Digital Design Unit at Darmstad. And thanks a lot, Pierre, for inviting. Super happy to be here. I've been watching all the events from the Bartlett Plexus event, and it's great to be here now. And let's say a little bit like the research which I've been doing in the last years in different contexts and with different people and in different locations. Revolves a little bit about an idea which I found really nicely expressed lately in a book which just came out this year from Doctorow. And it's a book in which Doctorow talks about this utopian society in which technology and humans are kind of working together. And what I find interesting is that it's not this super futuristic idea where everything is merged, but it's a much more, let's say, DIY way of looking at technology. And so it's this idea that a building actually has a sort of a code, and the building is not entirely built by machines, but it's a collaboration between humans and machines, and somehow sometimes the building tells humans, hey, what you're doing is wrong, and sometimes the humans propose to the building, hey, that's what we should do. And so somehow this is a little bit the background of what I've been doing in the last years, and I've been dealing a little bit with a bunch of let's say, dialectics between terms, and I'm going to try to go through that and show them with some projects. And one of them is the contradiction which exists between today's digital fabrication means, which, despite being digitally controlled by computers, they're still mostly analog, meaning they just process materials in a continuous way and not reversible, versus the idea of digital assembly, where things can be assembled and disassembled. And then the second idea is the idea of high tech versus low tech. And so there's a lot of possibilities of combination to say sometimes high technologies allow to have more low tech approaches, or other times intelligent design enables to have results which resemble high tech results by using low tech technologies. And lastly, the last element which I'm talking about is the idea of closed tools versus open toolkits. And so this has to do with the idea of from one side building tools which are enclosed and try to solve all the problems of the world into one, versus instead trying to work with small parts of a toolkit which, despite being really good at doing just one thing, they're made to intercommunicate and allow to build more complex and interactive workflows. So the first project which I wanted to talk about is, let's say, my late nights project in the last few months, and which I hope to release in 1 or 2 months. And this is a Grasshopper plugin which is called Coral, which is trying to enable voxel-based modeling within Grasshopper. So the idea is, if we want to allow collaborative design over several elements, we have to have tools which allow to model not in a continuous way, but in a discrete moment. And so we are able to work with separate entities. So the idea is, a voxel is nothing more than a three-dimensional pixel, and as a pixel, we can store information into that unit. So we can store material densities, color, any kind of properties, structural properties, transparency, and so on. And then we can process this volume to kind of construct this geometry. So the way in which somehow this works is we can start from a basic geometry. So if you look at that cylinder and you would build that cylinder in a standard CAD program, so for example with Rhino, you are not modeling the whole volume of that cylinder. You are just defining where that cylinder starts and where the cylinder ends. So you're just modeling the outer surface. While instead, if you convert that to a voxel model, you are actually modeling every single point in that space, and so you are able to control the volumetric properties of that. And so this approach, while it seems a little bit more complicated from a certain point of view, has a lot of advantages. So for example, if I want to offset the volume, it is an extremely easy operation. So no matter how complex the surface is, we are just moving on a distance density space which defines where that surface is. But then also what we can really easily do is we can construct much more complex geometries using continuous functions. So for example, this is a gyroid, or this is a Schwarz surface. And then what's interesting about this is that it also enables a whole set of operations which are much closer to operations that you would do in a photo editing software, so it's something like Photoshop. So for example, it's really easy to blend images, so we have one image at the top and one at the bottom, and we can blend them together. Or it's really easy to create masks. So we have this gyroid surface which you can then really easily mask and create these structures. And so that's a little bit how all these tiny things are created. They're really terrible because I just took them out of the printer before running here. So, but what's also interesting is that if we can control the geometry of the structure at the macro level, so for example in this case with a cylinder, but then we can control it at the micro level with, like, for example, periodic functions. What we can do is we can build structures like this, which by controlling the density of this, we create something that can be actuated and can somehow bend in a certain direction. And so we can somehow design gradient properties within the materials which are not homogeneous and continuous. And so, of course, this is some of the examples. A lot of the work which I'm looking into is also to enable the possibility of using such techniques on low-cost 3D printers. So there's a lot of research in voxel-based modeling which mostly targets, so for example the work of Neil Yoxman, which mostly targets high-end multi-material printers, so printers that cost $500,000 or things like that. But I think there's a lot of interest in looking into applying the same logics and the same techniques for design onto much cheaper machines. And so this is some examples. So that's, let's say, the starting point for this thinking about distributed modeling in space. However, despite the fact that I'm doing this stuff because I'm enjoying it and I think it's relevant, I have some issues with that. And so one issue is what I would call, so to say, Cartesian domination. So there's this idea in which x, y, z at exactly 90 degrees from each other define the world. And so when we are working with voxels, a voxel is always this cube of space which is in 3 directions. And I think that's a little bit limiting because there are possibilities to work with other distribution of space which are not necessarily based on this Cartesian space, and this can give other possibilities and other research. And so, and the second problem which you see is that it's like all the problems that come from 3D printing. And so, what's great about 3D printing is that we can customize, as I said here, we can even customize the internal of the material, not just the shape. But if we combine that with the fact that the process that transforms material in 3D printing is not reversible, so it gets material, it transforms it, and then we cannot really transform it back, or it's really complex to do that. And we think about the fact that the final product that we get, it's not really adaptable. When we start thinking about scaling up this process to the scale of architecture, well, there's a lot of questions that come. So most of the applications that we see about that is like creating these gigantic monolithic shells which are super adapted for one specific use or not adapted at all, so then we go back to standard examples. And so the idea is, couldn't it be that there's maybe a smarter way to think about creating buildings in an additive way, which doesn't necessarily involve creating a process that is non-reversible. And so the reason why 3D printing has a problem is that if we look at all 3D printing technologies, no matter what they are all, as they're called additive technologies, they are all additive. So meaning that they are all based on the fact that I get something, particles, a powder, a filament, and I process it in a certain way so that I can glue it together, and that's going to be glued together forever. So the question is, and that's like pretty much the focus of my research in Darmstad, is can we have another way to work on that? So is it possible that we work with a process that is additive, so which binds together particles, but which doesn't bind together particles in an irreversible way, but which works with the reversible connections? And also, can we also think that those particles are not necessarily at the micron scale, but they're at a scale that could eventually be manipulated by different kind of processes, as well as could be assembled and disassembled by humans? And so, thank God I didn't have to invent that, but there's somebody that is doing research on this since quite a long time. So the Center for Bits and Atoms at MIT is looking at a concept that is the concept of a digital material. And so a digital material is a material that is composed of parts that are discrete and have discrete positions in space. And the best example to describe that is the Lego brick. So why the Lego brick is so great? The Lego brick is so great because despite the fact that a small child has a positional capability of probably a few centimeters, so the repeatability of a process for a kid is really small, the fact that the Lego brick is designed with connections that facilitate this allows a kid with really low precision to build structures which have submillimetric precision. And so I thought that that was quite interesting thing for architecture, especially when then we think about the whole issues that come with tolerances, with the whole idea of like adapting a space and changing it. And so I started thinking, could we do that? And the first problem that I faced was that, well, there's not really a tool to do that. So what I've done is I've been developing a small crossover plugin which is called Wasp, which does exactly that. So allows a designer to build objects made of discrete parts, combine them together, and design in a discrete fashion. So the system on which this relies is fundamentally super simple. So whenever I want to define a part that creates a material, I just define the geometric shape of this part, as well as I can define what I call connections. So every part has certain planes that define where other part could go. And so what we do is we write simple rules that says, okay, the connection of part A that has to go with this other connection of part B. And so that's really simple, but then if we run that algorithmically in a large fashion, we are able to really quickly create this large-scale aggregation of parts. So these are a lot of the work of our students in Darmstad. And so what Wasp does in the background is taking care of avoiding collisions and all the problems that could emerge for this, as well as allowing to track a variety of assemblies. And so these are some of the examples, which are mostly, as you can see, generated with a totally random process. So I just start, I place a part, then I choose, okay, I put another one here, another one here, another one here, and I keep growing endlessly. So while of course that's cool to make a video to present this, when we want to start designing with such a tool, we have to start thinking that we might need to control the system a little bit more. And so the plugin offers also possibility of using a variety of techniques to create these aggregations. So one example is we can use geometries to drive aggregations. So we can use surfaces, volumes, curves, and use those to reconstruct those geometries out of discrete parts. Or, for example, we can use fields, which are nothing else than the same voxel spaces which we saw previously used in Coral, and we can reconstruct those spaces, those voxel spaces, out of discrete blocks. So, what we've been exploring a little bit in Darmstad as well is the idea that you can move really quickly from defining the connectivity between like a bunch of parts to exploring what's the effect that these parts have at a larger scale. And so what's interesting is that against the, let's say, conventional 3D printing aesthetic of the isosurface mesh, which is the same everywhere, these components have their own presence and have a certain spatial impact. And so they kind of allow to filter light in a certain way. They create structures that carry loads in different ways. And so it's quite interesting to kind of, all of a sudden, the material that constitutes this becomes part of the design in itself. But not only that, but one of the big advantages of working with these discrete parts is that as we know exactly in space where they have to be, so they have a unique space, a unique position, it's simplifying a lot any process of building structures with this. And that's because, for example, we can see here, there's this little detail with a small magnet that allows an exact alignment of this. And what's really interesting about this project is that the detail itself carries the load without using the magnet to carry the load, but still the magnet allows for error correction. And so, if we can do this for one component, what's quite interesting is that we can really quickly regenerated for a variety of geometries. And so here we can see some of the projects that our students have been doing. And so, of course, a lot of work goes into designing this part so that it corrects any possible errors and so that we avoid building up tolerances as we grow. But I think it's quite interesting to see students that started with no knowledge about algorithmic modeling, robotics, and so on, really quickly prototype that. Then, of course, those were the videos that students show us, but that's more what happens a lot of times. So, in reality, it's actually not that clean and not that easy. So, there's a lot of errors happening all the time. And the reason for that is that, at least when we started working on this was the standard way in which we were looking at it. So what we do is we define some modular aggregations in WASP, and then we get crazy to figure out how that sequence of components could actually be built without avoiding those crashes. And then we send out machine instructions to construct them. So one of the projects which I'm currently still working on is the idea of removing the middle part and making sure that all the fabrication constraints get checked directly while we are aggregating this part. So I'm placing a part and I'm checking if everything is fine when I build it. So I'm not designing a final object, but I'm already designing the process that builds that up. So and how we can do that? Well, for example, if we know that we have to place that part with a robot, we can add to the part the definition of what's the shape and the dimensions of the gripper that is going to place that part. And when we are placing that part in the assembly, we check if that gripper crashes with something that is already there. Or something else we can do is we can check for geometric configurations that make sense. So these bricks are slightly asymmetric. And so if I put the big part of the brick over the big part of the brick, that stays there. While if I put the small one over the small one, that falls off, and you saw it in the video before. But at the same time, if I place the small one when the big one is already in place, that also stays. So if we're able to model this, so we can see this is an aggregation when that has been not modeled, so we see that things fly, and then things are probably too close to be placed by the gripper, and so on. But then when we activate those constraints in the process of building, we start seeing that things all of a sudden make sense. So nothing flies, the order of assembly is actually the correct one, and so on. But at the same time, you also see that it starts getting, let's say, the space that the algorithm can search starts to be extremely structured, and it becomes really difficult to build structure that makes sense. So, for example, it tends all the time to create these gigantic towers because, well, that's stable. But, well, it might not be super useful. So, what we try to do is we've been trying to integrate, instead of trying to force the algorithm to look into this really complex design space, we thought, well, humans have a quite good intuitive ability to understand how to build a structure. And so we decided that maybe we could integrate human decisions within this assembly process. And so this is what we did is we equipped our robot with a super simple webcam. And that's, again, one of the big advantages of working with these discrete units is that as we know where they are, we don't need a super precise motion tracking system to know where everything is, but we kind of know where they are and we just need to more or less understand. And so what we do is we allow users to place markers over these blocks, and we link the markers to specific actions that the robot could understand. So actions like place a block here, or don't grow here, or grow more there, don't grow there. And so then when we rerun the project there, so what we can do is we can really quickly start placing some of the bricks, and then at some point we stop the process, the robot checks if everything is changing. User comes and says, okay, grow more there, stop growing here. The robot detects this and then starts the second cycle of placing bricks. And so there we see that there it's not growing anymore, and here it's growing a little bit more. Then we check again, and so on, and then we say, okay, now you grow enough. You grow enough there, grow a bit this way. And so the process keeps going. And so this is a little bit a process that looks at the brick as kind of like an independent unit, which has not really any characterization. So it's just really like block, and that's probably part of the reason why most of them I'm doing are out of foam, because they're light, easy, and cheap. But the idea that is behind that is that somehow this basic repetitive geometry, which is discrete, is somehow an interface that allows to integrate different techniques and different material within one process. So, for example, some of our students have been working at the idea that for sure I can 3D print one of these bricks and use them, but something smarter than I can do is I can 3D print a mold, and then I can put silicon there, and then use that mold to build these blocks in a variety of ways. And so not only that, but I can also 3D print parts of that block so that I can build a block made half of it of one material and half of that of other material. And so what was really interesting is that with this like little kit of parts to build that, students were able to build a variety of different modules. And not only that, but what they've been doing is they built this little scale which scales the brick in 3 different points and tells us where the center of mass of that brick is. So why do we need that? Well, these bricks is supposed to cantilever over each other, and if the bricks are all made of the same material, I can cantilever once, and then the second time this brick will fall. But if instead the weight of the material can change, what I can do is I can go, so build them at the block, and then I can start cantilevering, and since half of the brick is heavier than the other half, I can build structures which otherwise would not be possible, and so I can always have the weight so that I can build a cantilever out of these bricks. Other examples which we've been looking into is if I'm building these blocks out of, for example, a cast material like in cluster here, we can use magnets and like changing the polarities of magnets to define what can connect to what. And so all of a sudden, I don't even need a guide anymore to assemble this, because what can be connected to what, it's automatically encoded in the positive-negative alternation of the poles. And lastly, this was an older project, but in which we have been looking into if I have these units, so in this case, the units were not repetitive, they were parametrically generated, but if I have this unit which have discrete and define their boundary, can I go and explore how the interior can change? And so we developed a workflow using Grasshopper and Silkworm where we could automatically control the density of curves which were inside the piece, and then we choreographed this printing process that generated a differentiation of the density over that. And we were working with a designer from Milan, and the biggest question which we are still looking at is how do we go from this one, which already takes 70, 80 hours of printing, to something like this, which takes probably a few thousand hours of printing. And so, of course, the option is we buy 100 printers and we do it. But another idea which we are looking into at the moment is if we have this geometry, which is predefined and it's always going to be the same, we can actually think of a distributed production network. So we can think of allowing users to customize each different part, ship them on the site, and then build up this crowdsourced fabrication process. And we've been exploring the same ideas a few months ago in a small installation that we did together with Hen in Berlin, and where we looked at a similar idea. So can we have a structure which is predetermined, but where then each of these patterns is unique and is designed by a user, and we find out a way to compose them so that they still somehow create a structure which has a certain design option. So what we have been doing is we have been allowing users to use their voice to model something, and this voice was then translated into a wave which we then use to hot wire cut a block of foam. And the characteristic of the voice of each user determine the geometric characteristic of this panel. So the peak frequency determine the rotation, and while the different frequencies determine this wave. And what we've been looking at is, could we then cluster those modules in a certain way so that we know that higher pitched voices kind of come together, as well as could we look at trying to create continuous lines by matching changes in the orientation of these bricks. And so the idea was really that without pre-designing the final output, we could have like a contribution which we could not control, but which we could still fit within certain parameters, and then we could use to build a structure that, besides not being pre-designed, still had a certain level of design logic. And so during the course of the exhibition, we saw that somehow these lines emerge, and then we have clustering of higher pitch voices. And so, besides not designing this process, we still managed to build a gradient structure over this, which looks like it would have been designed. And so, a little bit all these different parts which I've been looking at try to understand a little bit how this discrete logic of fabrication could allow a model of production which is not anymore closed. So the way in which design is still seen today, despite a lot of advances in design to production workflows where we bring in constraints within the design domain already, but still, we're still in a world in which there's a design phase which at some point stops. There's a specific cut, and then fabrication starts. And so I'm really looking forward to figure out methods as ideas where this cut all of a sudden doesn't exist anymore. And a little bit back to the first reference to Cory Doctorow, really this idea of having a continuous process of design and fabrication where spaces can be adapted, assembled, and disassembled together by designers, users, and so on. And so these are the people that have been working with me on this project, and they've been all great, and I'm really happy to have worked with all of them, and that's it. So thank you.
Any comments? Questions? Debating ideas?
Yeah, I'm super interested in trying Coral. So when will it be released? Soon?
Yeah,
Okay.
Depends how much is needed.
Yeah, that's a good criteria. And
I mean, there are other tools. I mean, that's not the only tool.
So that's the second part of the question. How does it compare to Monolith, for instance? Or
It compares to Monolith in a sense that it's probably slower, quite a bit slower than Monolith, really honestly. But the aim which I'm trying to follow with all the tools I've been working on, and the cost is the same, is I'm really looking, first of all, in like having open source tools, because I fundamentally believe that I actually started with the idea of using Monolith for what I wanted to do for Coral. And then I wanted to do a couple of things that Monolith could not do, and Monolith is a closed software, and then I was like, what should I do? The second thing that the main difference which I would say is there with Monolith is the fact that Monolith is specifically and directly pointed exclusively at 3D printing. So the way in which channels are defined is a channel can be material density or can be RGB, and that's it. Coral tries to be absolutely agnostic about what you want to do with it. So any voxel space can have as many channels as you want, and you can carry them all around, and then you can break them out, break the values out, do something else with them, then break them in again. And so the idea is really to try to have a less closed up and structured tool, and more like an open workflow that can be adapted to what users want to do with it.
exciting.
There is something I have, it's not a question, but it's a comment perhaps, because I like to, even though I try to have quite of an open iteration, I had a certain idea in mind when I was making this panel, which could open the debate, or perhaps some other thoughts. Is that what's interesting in your work? It's also very representative in a way of a certain idea of how to apply discretization to an architectural research. And there are many ways to approach this science, right? I think we will see it differently Sine's work, also in Florian's presentation, perhaps, and certainly with the work of Guillaume, which is working at a completely different scale. But somehow, for me, in your work, it's clear that you use discretization as a direct geometrical application. And that is your answer to tackle the problem of assembly logics, if I'm correct. You can tell me I'm completely wrong. I'm just thinking out loud. So this is interesting because this is a contemporary problem which can be thought through many, many ways. I mean, this is always a problem of continuity in thinking. In architectural thinking, but this is also the problem of architectural projection in architectural thinking. So projecting an idea into architecture is, in history, it's always producing either huge mistakes which are making completely new outcomes which have nothing to do with the original ideas which were coming from philosophy or art. So we can think of humanism, for example, in Renaissance, which we can put something completely different in architecture. We can think about constructivism. It's all through architectural history. So today we have a couple, I would say a dozen of ideas which are coming from different fields and which are either directly projected or modulated into architectural thinking, and one of them is actually discretization. So a few days ago there was a colloquium. So a few days ago there was a colloquium organized by Christian Girard, Emmanuel, and also Jérémy Lecomte and Philippe Morel at the Digital Knowledge Department. And they were, I think, also trying to tackle one of these topics. So I wasn't there for the whole debate, but it's also a very active discussion. I think your work is thinking about also this thing. So yeah, thank you for the presentation. Do you have any other comments, or should we?
I just have a question, which is a really open question. Do you look at past examples of these kinds of research, such as David George and Lish, for example? Is it something that fuels your own?
Yeah, sure. I mean, let's say the main idea that was behind all this work was, let's say, in a sense, it's really, like, say, removed from, let's say, real problems in a sense. And like a bigger step was to look at much more like really the geometrical principles that sits behind that. So there's a lot of research also like in the design field that goes towards all this research. And let's say I'm interested in that, but I was like, at least the way I saw it is I kind of saw it a little bit, at least for me, from a step back from this kind of research. And much more, like looking at the principles. So most of the designs I'm showing are actually not mine, are from my students, which I think they're much better designers than me. And so that's part of why I think there's a lot of research which is in this field and just been applied, which is inspiring all the work I'm doing. And so, for example, also the work of like physical peers in like structures and so on. But at the moment, I'm like more and more going back into looking into like geometry and mathematics research in this field. Also for the simple reason that the plugin is still too slow. Which then it's about understanding how these things are designed.
I have a very practical question. You said when you were presenting the bone-shaped bricks, which were fitting together, and how did you manage to, in the grasshopper model, how did you manage to know that it was holding in place? Which kind of tools did you use to know that everything was working?
Do you want to show it?
And it's basically a question that could be attached to all the designs that you've presented.
Yeah. So
no, the previous one actually. Yes, this part.
This one. Yeah.
Yep.
So there's two approaches which are there and which I'm looking at the same time. So the approach which was used in this project is it doesn't take into account any statics or like dynamic simulation of physics. It just looks at purely at geometric configuration. So I'm just looking at, let's say, this super basic thing. So as soon as I know that things interlock, they have a certain stability in themselves. And the idea is that if the connection is strong enough to hold, the idea behind working with discrete materials is that the connection will break before the break all the time. So especially when I'm working with dry compositions. So that's one option. And that's what I've been using so far in all these assemblies. What I'm looking at the moment is I'm looking much more into using rigid body simulations to understand how those things work. Although generally speaking, rigid body simulations are a disaster in modeling interlocking parts.
So, sorry, what did you say?
Rigid bodies, generic rigid body simulations are either extremely slow or extremely bad at calculating interlocking shapes. And so that's why, at least in this point, especially because I thought that was really good for users, it's much easier to understand like how the geometry of the interlocking works.
Yes, but either kind of a general static balance, just so it doesn't.
Yeah.
So you made this computation, not the interlocking part, but just.
In this case, no. Like here it wasn't done, so here it's just like relying on like purely local interlocking parts. But what I'm looking at is like understanding exactly the static balance of it. That's actually what we were doing in this project. By knowing where the center of mass of each brick we always made sure that the center of mass of the next brick would be within the previous one. And so that's why we were able to build the structure here.
Thank you.
Any other questions?